So this search algorithm you can do in log n time. Yesterday you saw that if you're finding a max or a min in a list of n elements you can do it with n minus 1 comparisons. But if I want min and max, it's a very simple 2n minus 2 algorithm, but you can do it better with 3n by 2 minus 2 comparisons. You can sort in n log n time. There are n square algorithms. Kritika mentioned a lot of n power k algorithms, 2 power k, all these things, and she even mentioned there are problems where you can do with n power k, but we do not know whether we can do better, right? So can we do better is the question we will be looking at here. I mean, can we do better is the constant quest in algorithms anyway, right? The moment you design an algorithm, you want to know whether you can do better, right? So in particular, you want to know when you reached your limit, that you cannot do better, right? So today, at least in my lecture and in the themes that will follow, we're going to actually answer no unless something happens, okay? In fact, for some problems, we will actually say, no, you cannot do better, this is the best. For some problems, we'll say, well, if you can do better, then something happens, right? And that's going to be the theme, right? After all, what does NP completeness tell you? If people have seen NP completeness tells you what? There are problems you cannot solve in polynomial time unless what? Unless p equal to np, right? So similarly, in the rest of this lectures, you're going to say unless ETH is false or some such big words you're going to hear about it, right? So, but the point of all this is to understand the limitation, that whether we have reached the limit. Can we not do better than this? And how do I even argue about this? That's all we're going to see, right? So then once you say, can we do better? No. Then you ask, is there a way around, right? And we will say, yes, maybe you can do some parameterization or approximation or some other things. Okay, so that's what this whole school is about, right? Because in case you were wondering, what is non-trivial algorithms doing in a school on NP completeness? Well, the whole point was to give you some context. It's like you've seen movies where they don't necessarily start with the title, right? Sometimes the movie starts off and then after 15 minutes, the title flashes, the director, everybody comes. So it's like that. So here is the title slide, title talk in some sense, where we're going to say that there are problems we cannot do better than what we have seen so far unless something happens. And this is something I may not do it. You'll see it in the later lectures that, yeah, there are ways around it. These are NP completeness and algorithmic approaches to deal with that. That's what it's going to be. So in particular, I will in this essentially only talk about these things that you cannot do better than whatever bounds, non-trivial bounds you have achieved. Okay? But let's start with, suppose somebody says, oh, maximum. We know how to find it in n-1 comparisons, but somebody says, I have a very clever algorithm which can actually find the maximum of a list of n numbers in order log n time. Can you believe the person? Why not? You shook your head. Yes. Why do you think? So somebody says, I can find the maximum in order log n time. So log n doesn't even give you enough time to look at the input. But binary search, you can do it in log n time.
That's sorted and we don't need to know.
In fact, the whole point of binary search is to make sure I don't look at the whole input. I don't want to, and it's already sorted and things like that. Okay. But maybe n by 2 comparisons is enough to find the maximum, because that gives me enough time to touch every input. Right? Do I really need n minus 1? Sorry? No. Let's come back to the problem. I have a list. I want to find the maximum, unsorted. Of course, if it's already sorted, constant time, right? It's unsorted. I want to find the maximum. You said log n, no, not possible, because you really need to look at every input. But maybe n by 2 comparisons is enough to, touch every input. Do we really need n minus 1? Do you believe n minus 1 is necessary? And if so, how do I rigorously argue that? Do you understand the question? It's a very nice, because we are talking about something against every algorithm. So far we've been designing algorithms, and here is an algorithm, here is a complexity, we've argued about it. But now I want to say no algorithm can do better than this. That's a statement about all algorithms, and how do I say it? How do I rigorously argue this? Right? This is the question. Okay. So similarly, I want to argue that if you have a sorted list and you are doing only comparisons, you cannot do better than log n. How do I argue this? Okay. So there is an interesting formal way of arguing this. This is based on what are called adversaries. So this is essentially something along the lines of what you said. You really need to touch every input, otherwise an adversary can do something that maybe your algorithm is wrong or some such thing. But before I get into that, let me ask this question. Can somebody give me a formal logical statement? So let's say you can sort in n log n time. Everybody agrees? Given n numbers, you can sort in n log n time. Can you say that precisely in a logical sentence? That we can sort in n log n time. What is that? Why? How? Why? Give me a logical statement to validate this statement that you can sort in n log n time. Logic, right? There exists for all, use such constructs. Why do you say you can sort in n log n time? There exists an algorithm. Good start. Okay, let's start. There exists an algorithm. Yes. That. That for every input of size n can sort it in at most C log n time. Cn log n time. Right? So in general, if I want to say I can solve this problem in f of n time, let's say, right? So what does that mean? That so my problem pi can be solved in f of n time. Means in that logic, there exists an algorithm that for all input of size n can solve it, whatever that solving means, that depends on that problem, in f of n time. Okay, so that's what it means by pi can be solved in f of n time. Okay. Now if I want to say pi cannot be solved in f of n time, because that's the kind of question we want to answer, right? Because that's what our lower bound question is. If I want to say pi cannot be solved in f of n time, that means it's just a negation of this statement. Tell me that. So negation of this would be for every algorithm, yes, there exists an input that takes more than f of n time to solve. Okay? So that's what the adversary is trying to do. The adversary is trying to give for every algorithm some worst case input on which this algorithm will take long time. Okay, so that's what an adversary argument is. So let's start with this simple problem, this binary search problem, right? Let me convert that into this problem that I think of a number between 1 and n. You have to ask me questions to find the number. How many questions would you ask? Can you not answer in one question? What? Yes, no? What is the number you ask? I'll give you, right? Okay, so I think of a number between 1 and n. You have to ask me questions, yes or no questions. Okay, now I have qualified to answer, to guess my number. Now what do? There are only 2-3 people answering. I want more people out there. Yeah, so what is your first question?
Maybe is it less than 100?
1 to n.
1 to n, yes. I tried to bound the range.
Yeah, what is your first question?
Is it less than 100?
Less than n by 2,
Yeah.
right? Binary search. So you ask less than n by 2. Depending on the answer, you will go and ask n by 4 or 3n by 4 and keep going. And you all know, if you have learned your binary search analysis correctly, you can guess my number in log n many questions. Okay, everybody with me on that? Okay, so now let's turn the question around and say, I think of what, my aim is to force you to ask a lot of questions. Okay, that's exactly the adversary's point. Adversary is trying to make you ask log n questions. I don't know what algorithm you are going to follow. So what number should I think of? What number should I think of so that I can force you log n many questions? Okay, that's exact, because I want to prove that any algorithm, this is important, to guess my number will take you log n time. So what number should I think of? First number, extreme numbers, okay. Any other? No, I have to play by the game, rule of the game. I am allowed to guess only between 1 and n. That's his point. If you say extreme, first number, you don't know, you might ask that as the first question. You're not necessarily playing binary search. We are not saying binary search, we are saying any algorithm must take log n time, right? So I have to think of a number which will force you to ask log n many questions. So now what he said, can you repeat what he said? Yeah. Right. Exactly, right? But now comes, let's look at this logical statement. It says, for every algorithm, there exists an input. So that input will depend on the algorithm. I'm not necessarily claiming there is a universal input for every algorithm. You tell me the algorithm, I will give you the input. So the way to think about it is that, oh, I have a number between 1 and n. You write down your algorithm, give it to me. I will look at it. For this algorithm, this is the number I am thinking, which will take you log n questions. Okay. If you change the algorithm, I'll change my input, right? Because this input depends on that algorithm. Okay. So let's come back to this. Still, I don't want to see the entire algorithm. I don't even need to see the entire algorithm. I can answer online dynamically so that I can force you a lot of questions. Let's make the range 1 to 100. I think of a number between 1 and 100. I don't know what question you are asking, but I want to force you log of 100 many questions, right? So let's say you ask, is the number bigger than 34? What should I say? Right? First, observation. I don't have to think of a number. I will play by the rule. As I go along, I'll make up my number. Okay? Because this input depends on your algorithm. So why should I give my input right away? Right? So I will think of my number based on the questions, because my job is to tell you that for any algorithm there is some input which is bad. So you ask the question, is it bigger than 34? I'll think about it. And even if I had thought of something less, I'll change it now, right? Because my job is to force you. So I will say no. So now we talk about an adversary strategy. So what should be my strategy? Can you generalize this and tell me, in general, for 1 to n, you're trying to guess my number. What should be my strategy? How should I answer the questions? The questions are comparison questions. Questions are, is it bigger than, smaller than? That's all the rule you're allowed to ask. How should I answer? Go to the maximum range. Yeah? What do you? Sorry?
When you answer less choices should be eliminated.
Correct, exactly. Both are saying the same thing, right? So larger range should remain. Fewer range should get eliminated. That's it. So now I can force you log n many questions, because the same upper bound recurrence for binary search, you can turn it around. How can I force you log n many questions? Because in one question, you can throw away at most n over 2 elements, because I ensure that at least n over 2 remains. So if I follow that strategy, I don't know what algorithm you are using. It may be binary search, it could be anything arbitrary, but I have a strategy by which I ensure that I will answer. My answer should be consistent, because I cannot say once when you say, is it less than 34, I say yes, and then you ask, is it less than 50, I cannot say no, right? It has to be consistent. But I ensure that at least half the range remains, so I can force you log n many questions. That answers this point, that for binary search question, at least for every algorithm. What algorithm is a set of questions you are asking. I don't have to look at the entire algorithm to provide your input. I will just dynamically have a strategy to tell you that for every algorithm, I'm going to say, you ask the question, I will make sure. So my recurrence now would be T of n would be, or it's greater than or equal to 1 plus T of n over 2, because I ensure that at least half the range still remains. So this would ensure that omega log n comparisons are necessary to guess my number. Okay? Any algorithm. For every algorithm, there is some input. That clear? So this is a formal, rigorous way of arguing this, right? So now let's come back to min or max. Again, it's an adversary. Okay? So what are you doing? You have these n numbers. You're going to keep asking questions. Oh, let's say A1 to AN are the numbers. You'll say, what about A3 and A7, which is smaller? And I'll answer something. Okay, I have a sequence of numbers in my mind. I will answer accordingly. Consistent, honest to God, I'll just keep answering these questions according to that. But suppose you asked less than n minus 1 questions. What can you say? So in one question, how many numbers can you eliminate out of max? Let's say we are doing max finding. We're finding max finding. You're asking about A3 and A7, and I say A7 is bigger. What can you gather? A3 is eliminated. So in one question, you can only eliminate one number. So if you have asked less than n minus 1 questions, there are two numbers in contention. I have a choice now about which I can make any of them bigger. Right? Because if you say at the end of it, this is bigger, I will say no, this is bigger. And it will be consistent with whatever I answered. Okay? I hope it's clear. Otherwise, Mano had a slightly different argument. You want to tell your argument? For max n minus 1. Yeah. Yeah. Right. So what you do, think of a graph on n vertices. A1, A2, A3, AN, n vertices. And anytime you ask a comparison, I will draw an edge between those two vertices. Okay? It doesn't matter how I answer. I'll be answering consistently, but I'll draw an edge between the pair of vertices. Now, if you asked less than n minus 1 questions, that means there are only less than n minus 1 edges in the graph. What can you say about the graph? N vertices, less than n minus 1 edges. So, disconnected. That means there are at least 2 components in the graph, and so which means the algorithm has not learnt anything between a number here and a number here. So you have a choice of making either one of this, topmost guy the largest number. Okay. So another way to phrase this again is that for every input, for every algorithm, there exists an input that takes greater than fn time to solve, or there exists input such that if algorithm takes less than or equal to fn comparisons time, then algorithm is wrong. Right, in the max finding algorithm, so I have 2 components. So the algorithm learnt, and there is this. Maybe there is even 3 components. So it learned nothing between elements here. So if it says this is the largest based on whatever questions it has asked, I can say no, this is the largest, and I would be consistent with all the answers I gave. Okay, so that means I can prove the algorithm wrong if it made less than or equal to n minus 2 comparisons. Okay, good. Now let's get back to this 3n by 2. It's a little, it is amazing. If I really want to show that you cannot do better than linear time, that's easy, right? You all talked about it. You can't even look at the input otherwise. But what is beautiful is that you can actually show 3n by 2 minus 2 is the best you can do for finding min and max using an adversary argument. Yeah. No, there exists an input. It continues to be there exists an input such that on that input the algorithm must take long time, which I rephrased it as if the algorithm took less time, then the algorithm will be wrong. So what is that input? So if the algorithm says this is the maximum, I will create an input in which this is the maximum. On that input, the algorithm would say this is the maximum, it will be wrong. Okay? So we have seen search, right? I have an adversary strategy. Every time I answer in a way that at least half the range remains. We have talked about max or min. Now let me talk about min and max. Okay. So again, interestingly, both algorithms and the adversary have the same information. They have learned the same things. It's not very different. It's just that it's like a game. Both of them are playing a game, very tightly moving game. Okay. So what is the problem here? I am given some n input. Let's say A1, A2 up to AN, and I want to find min and max. Okay, so let's again, algorithm starts asking comparisons, adversary answers the questions, but adversary has to answer the questions in a very clever way. That's all we've seen. But what is this clever way? We will see, right? So let's understand how can you sort of capture the knowledge of the algorithm at any point of time to our purpose. My purpose is to find min and max. Okay. So let me use the language of winning and losing games, right? So when in a comparison, one element wins and another element loses. Okay. So finally, when the algorithm stops and I found the min and max, what does that mean? When do I stop? In the language of winning and losing. In the language of winning and losing, I start comparisons. Eventually I stop. I found the min and max. What does that mean? What can you say about how many elements of what type? Max is 1 over all elements, yeah. And what about the other elements? The remaining n minus 2. Yes. So, but I don't know max and min, but I'm going to say there is one element which has won all the games it has played. There is one element which has lost all the games it has played. And the remaining elements have lost some and won some. So they are not candidates for max or min because they have lost some games, they have won some games, so they are not candidates for min or max. But everybody else belongs to this category, lost and won. But there is one guy who has only won all the games, there is one guy who has only lost all the games. Then I know I can declare I found the min and max. Okay? So I'm going to now capture the state of the algorithm into 4 sets. Okay? The 4 sets are L, W, LW, and N. So this is a set of all players who have lost all games played. These are won all games played. They've lost some, won some. And these guys have never played any game at all. Okay? So you can see the board from there. Is the board visible? Maybe you don't care. Oh, you woke me up. Okay. What about this? This is visible? Okay. So at any point of time, there are n players, and I'm saying I can partition the players into 4 sets. Those who have won all the games played, those who have lost all the game played, those who have lost some, won some, and those who have never played. Okay? And let me denote by the small letters the size of these sets. Okay? Now when the algorithm stops, so let's think of it as a 4 tuple. 4 tuple. Okay, so let's say L, W, LW, and N. When the algorithm starts, what is that 4 tuple? Sorry, I shouldn't use the word N, use NP or something. Different NP. Because there are totally n players. When you start, so to me this is the state of the algorithm. At any point of time, I remember this 4 tuple that tells me both what the algorithm and the adversary know this. Okay, so when I start off, yes, 0, 0, 0, n. And when I finish, what should it be? 1, 1, n minus 2, 0. Okay? So think of it as this is the state of the algorithm. I want to start from 0, 0, 0, n and end at 1, 1, n minus 2 by playing games. Okay? Now, the algorithm's job is to get quickly from here to here. The adversary's job is to delay it. Make sure you don't go very fast from here to here. Okay, this is the tension between algorithm and adversary, and we play this game. Okay, so now once you formulate the state of the algorithm this way, the adversary strategy is very clear because adversary strategy is to slow down the movement, right? So now algorithm asks a comparison. It picks 2 elements and asks, okay, which is bigger? Well, then I will look at it and say, which set do these sets belong to? These 2 elements belong to, right? Well, maybe, so it asks for a comparison x comma y. Maybe x is in L and y is in W maybe, okay? As an adversary, now I have to tell you who is the winner between these two. What should I say? I want to make sure that these set sizes do not change drastically, because that's how I can delay the whole thing, right? So for example, I have a choice. I can say X wins or Y wins. If I say X wins, what happens? If I say X wins, capital L reduces, what increases? LW set increases by not 1. Because now the Y also loses. So if I say X wins, Y loses, so LW increases by 2, right? So let's say this is LW, LW, and never played. I don't want LW to go fast from 0 to n minus 2. I want to delay it, okay? But if I say the winner who has been winning wins and the loser who has been loser loses, nothing changes. Well, L and W, no, nothing changes. Nothing changes, right? The set capital L doesn't change, capital W doesn't change, LW doesn't change. So my strategy would be to say L loses, X loses, Y wins. That's all, okay? So now you can formulate every comparison how you answer based on this kind of a strategy, that I don't want the movement from here to here go for very fast. So think of, yeah, so here adversary will say X loses, Y wins. Because if I say the other way, LW will increase by 2. Okay, but if I say answer this way, LW, N, nothing changes. The state remains the same, which is a good thing, because I don't want fast movement. Okay, now you can enumerate all possible things. So for example, if X is in NP, Y is in NP, what should I say? Somebody here? Yeah? It's the same either way, it doesn't matter. I arbitrarily answer. Both have never played. I'm going to say one wins, one loses. So L increases, W increases. But I have no choice. I have to say one of them wins, one of them loses. So I'll say arbitrarily here, I don't have to think anything. So I will say, I could say X losses. So now, so what do I mean? So this, you can write down all the strategies. So let me write down the effect of my adversary strategies. So if X is in NP and Y is in NP, then I say X wins, doesn't matter, Y loses. So what happens to LW, N? The N will decrease by 2, N minus 2, right? Because never played count decreases by 2, LW nothing changes here, this increases by plus 1, so maybe I'll say minus 2 plus 1, nothing, no change. So you can write down, enumerate all possible comparisons. Algorithm is just asking a comparison. I will answer based on where these two elements are, which set they belong to, and I will answer in a way that there is very little change when you go from one state to another. Okay, so let's say if X is in W and Y is in W, how should I answer? Arbitrarily, because both of them have won all the games so far. I answer arbitrarily, but what happens to the effect? LW increases by 1, right? LW will increase by 1 because one of them who has been only in W now has gotten a loss. W becomes -1 here, and the rest remains the same. Okay? So you can write down and write this huge state diagram of the entire algorithm. This is the knowledge of the algorithm and the adversary, both, right? There's no cheating happening. They all know the answer, entire information. Only thing is their goals are slightly different. Okay? So write down this entire state, and now you want to say how fast can you go from here to here under this adversary strategy, which is the same as what is the length of the shortest path in this huge state diagram by this adversary strategy, right? Because now you can draw an edge between every pair of vertices. I am here and I ask a comparison, where do I go here? I go to a different state. Sometimes I may stay in the same state by making this a comparison. And one can argue that whatever algorithm you saw yesterday for that 3n by 2 is more or less optimum. Because, so what you do is, okay, how do I get from here to here? One way to get is you pair these guys, right? This is essentially you're running a tournament on, so you start with never played games and pair them up. You have all the winners, then do WW games, WWWW, and you get this entire thing done. And how many comparisons? You will do n-1 comparisons. Right? Because in this WW games, so the best strategy is to play this WW games. What happens is this LW increases by 1. Okay? So you make something like n-1 such games, or no, let's do, okay. So what do I do? So I go from here to, this becomes 0. Okay, so in about n by 2 comparisons, by just pairing all the new, never played elements, you keep comparing, and in about n by 2 comparisons, this becomes 0, and you would have had some winners and losers, right? So now you play the winners again, and you will keep on increasing this. This guy, so this, in this whole process, this remains 0. Now after that, you play WW or LL kind of games. This will gradually increase up to n-2. So the total number of comparisons, the best strategy would be n by 2 plus n-2. Okay, so n by 2 to get from here to 0, the last coordinate, at that point, nothing changes here. And then n-2 to make this guy increase 1 at a time and come here. Okay, so I'm just sort of pushing things under the rug, but are there any questions? Yeah. So there is a pair in which there is a way I will answer so that you will go from here to here. Yeah.
Different answer will lead to different.
Yes.
So like this is like a,
yeah.
like
That's the state diagram. Yeah.
like what remember here.
Shortest path.
Longest path.
No, I want to give a lower bound for shortest path. I want to give a lower bound for shortest path. Because shortest path is what you can do. You can just move forward by asking me these questions. And I'm going to say that the way I will answer, that shortest path has a large length. Okay, so you are saying your state diagram is there exists an XY which will lead, and there exists an answer which will lead me here. There exists another answer which will lead me here. Right. Okay. Yeah. But the way I'm drawing the graph is,
like if this is a big graph,
yeah.
in your head,
Right.
and you are saying that in this big graph, if you're here,
I will
to
answer.
a particular
Yeah.
place.
You ask a question, I will take you here
Right.
by answering it this way. And so for any question you answer, I will answer to meet you there. So it's my graph in some sense. It's not
Which is a subgraph
of the whole big configuration graph. And in this, my graph, the shortest path has a lower bound. So the beauty of this lower bound is also it immediately tells you what a good algorithm is. Because a good algorithm, it says just do pairwise comparisons and make your n to get to 0 quickly. So that's like you do n by 2 comparisons. What you have is some who have won all the games, some you have lost all the games. Don't play the winners with the loser. That's a bad comparison because the adversary will answer in a way that the winner wins, the loser loses, and you are wasting a comparison. But if you play winner-winner, adversary is forced to make somebody lose. So your LW increases. Or if you play the loser-loser, LW increases. Okay, so that also tells you what the right algorithm is. Okay, it's very similar to how the binary search tells you that you ask the middle. That's your best strategy for an algorithm. And this lower bound essentially says that's what's the best. Okay. So there are questions, I think, in the problem sheet where something similar you apply for merging two sorted lists. Right? If you have two sorted lists, one of size n and another size n, how much time does it take to merge these two lists? Anybody? How do you merge? So you have a sorted list of, let's say, n elements, another sorted list of n elements, okay? And so on. It's a huge list. I want to merge these two lists. You've all seen the merging algorithm, right? How much time does that take? N square, n cubed, n plus n, right? Essentially n plus n minus 1 if you're very careful about it, because basically for every comparison you get one output. There are two n elements. The last one will come to you for free. Okay. Now, a problem asks you to show using adversary arguments that is the best, right? So that means you have to give a strategy for how do you answer comparisons, right? The two lists are A and B. Algorithm is trying to merge these two lists. Does it make sense for it to ask two elements of A or two elements of B? Because you're already told they are sorted. Okay? Feel free to ask, but you're wasting your comparison. So an algorithm will ask a comparison between some element of A and some element of B. You have to say, how do you answer? That is the adversary strategy, so that you stretch the total time. Okay? I think there is also a problem on finding the max second largest element and trying to show using some adversary that's the lower bound. So there are, so the good thing about adversary lower bounds is, first of all, you can show tight upper and lower bounds. Typically, you can convert that into an algorithm and show that that's the best. But sometimes it does not necessarily give you a, yeah, okay. It doesn't work. It's hard to come up with for complicated algorithms. Yeah.
For the second largest element, finding the largest second largest in n by 2 minus 2.
No, 3n by 2 by,
Minus 2 comparison.
no, that's not for second largest. That we did for max and min.
But there was in the assignment there was upper bound is there.
Oh, and then there is a tighter.
The tighter upper bound.
Okay, fine, okay.
So
Good. Now let's get on to, can you do better for sorting, right? Yeah.
Always like the adversary arguments that naturally give out some algorithms like
Usually, yes. But,
if it is tight,
yeah. Yeah, exactly. Yeah. So, I mean, there is always an easy n lower bound for even max and min, right? N minus 1 lower bound. Okay, you can create an adversary lower bound, which says that n minus 1 comparisons are necessary to find max and min. Of course, it is necessary just for max, so I might as well add to find max and min. Does that convert into an n minus 1 algorithm for max and min? No, right? So that basically our quest in algorithms is start with some brute force algorithm, keep on improving it. Similarly, we start with some simple lower bounds, keep on improving it and see where they match, right? That's what. And when I wrote earlier that can we do better? No, unless something, right? These are very, very few problems which are sort of unconditional lower bounds. There is not putting any condition. But when we get to NP complete or even others, we don't know. We can only say you cannot do better unless something happens. So it's conditional on something. Okay, so now let's move on to another lower bound technique. How do I show that you cannot do better than n log n for sorting? How many of you have seen this lower bound? Okay, 1, 2, 3, 4, okay. Okay. So first thing is, now that we have learned adversary, can we think of an adversary lower bound for sorting?
Can we at least give a lower bound for sorting?
Adversary.
It's a 10 and 20 and like just, and I'm not even expecting a log n, but like,
Actually, I think even n log n can be shown because if I say, okay, so I don't know what happens to the following argument, okay? No, so you do. So a comparison comes. What do? I say, if I answer this way, how many permutations do I eliminate? If I answer that way, how many permutations do I eliminate and keep, eliminate fewer?
so maybe we can,
Doesn't that immediately give you log n factorial lower bound?
maybe
Yeah, that is this permutation argument, right? So if,
the permutation we might not be able to see, but here this I can see because it's just.
I see. Oh, okay.
Transitive edges you can add. So as an adversary, I would like to
Minimize
minimize
the additional edges I get. But I know there is a nice simple, not simple, but some adversary lower bound for sorting. It does exist. It was some Fox paper or something, some 80s, somewhat non-trivial. Kosaraju Rao and some others, I remember. But okay, so back to sorting. So okay, we are all discussing that adversary lower bound is not so easy. So how do you then show you cannot do better than n log n for sorting? So there are about 3-4 hands went saying, you've seen lower bound? You? Okay. Do you remember how it works? Okay. Anybody else? Somebody new, not the same guys who are answering. Anybody else who has seen a lower bound for sorting that you cannot do better than n log n? Okay, so let's see. Let's say you have 3 elements which you want to sort. Can you give me a sorting algorithm? Don't tell me merge sort or quick sort. You have only 3 elements, A, B, C. Yeah, so what is the sorting algorithm? Okay, so if A is less than B, then if B is less than C, then output A, B, C, else, what do I know? B is greater than C, so C, A, both are less than B. Okay, let's assume all elements are distinct. For convenience, that's useful assumption. So at this point, I know that A is less than B and C is less than B, but between A and C, I don't know. So let me compare, right? So if A is less than C, then A, C, B, else C, A, B. Okay? This is if A is less than B. Now you have an else here and do something, right? In fact, 3 elements, 4 elements, 5, any sorting algorithm is going to look like this, right? It's just because, okay, any sorting algorithm which infers only by making comparisons is going to look like this. You have a question?
Like, I'm a bit confused with sorting. Why is it not like your search?
That's what I said.
It's like, no, I'm not-
Log n factorial.
no, it's like, so I maintain a list of all permutations.
Yeah, exactly. This is what I said. Every time I answer in a way that the number of permutations is at least half of what
that
remains.
always exists.
Yeah.
So this isn't
I think it gives you log n factorial. Maybe the issue may be that the time to, I mean, as a comparison lower bound, it should be okay. I think it works as a comparison lower bound. So I don't know then what that paper on adversary lower bound for sorting gives. Maybe it also worries about the time for figuring this out, because now I need to
figure out. Yes.
all the permutations, the number of permutations.
We can have a lot of time, right? We don't look at
That's why I'm saying if you take care only about comparisons, this should work. But if you also now say, okay,
the power of adversary.
yeah, limit the power of adversary, the
Some end
polynomial time or something like that. Yeah, I think so. I mean, but it's a good thing to check it out, what that lower bound paper
I
does.
just don't see any good, like,
Yeah, I think that's what I said. I mean, answer in a way that at least half the permutations remain. Yeah.
just like search.
Yep. Okay. Anyway, so adversary argument might actually give you, by the way, that gives you what bound? Log of n factorial. We still need to figure out why n log n. Okay, we'll come to that. So let me anyway give you this argument, because this is another lower bound technique other than adversary, which may be a useful lower bound technique. So what am I saying? I'm saying that any algorithm, any sorting algorithm which infers information by making comparisons should look like this. It's basically a bunch of if then else, if then else, if then else statement, which you can convert it into a tree, right? The tree will look like, I will compare A and B and say if A is less than B, then I compare B and C. And if B is less than C, I have my output. Otherwise, I make one more comparison and so on and so forth. So this is what is called a decision tree. And any sorting algorithm can be modeled like this, as long as it's making comparison. If your sorting algorithm says, oh, if this number is 27, do something, no, it doesn't fit into this model. Okay, the model of computation is you're making only comparisons between elements. Then you can map it into this kind of a decision tree. Now let's understand the properties of the decision tree, right? What do we know about this decision tree? How many leaves should there be? In factorial, because there must be one for every permutation, because the outputs are all permutations of the input. So there must be n factorial many leaves. And what is the number of worst case number of comparisons made by the algorithm? How does that translate to as of in this tree? Height of this tree, right? Tree, the number of nodes in the longest path from the root to a leaf is the height of the tree, and that is exactly the number of comparisons you are making to solve this. Because you do see that sometimes you can actually do 2 comparisons, you will get the output, but sometimes there may be 3 and so on. So the height of this tree, so what are the 2 observations you make? Any sorting algorithm can be modeled as a decision tree, having at least n factorial leaves, and the worst case time corresponds to height of such a decision tree. Now, if you have a binary tree with n factorial leaves, you can say something about the height of the tree, right? So again, an exercise for the tutorial, if you have not seen this, is that any binary tree on k leaves has height, yes, at least log k, maybe even more. Okay, how do you prove this? But you have to argue that's the shortest also. Okay, that requires. Or you turn around and say, take any binary tree with height k, how many leaves can it have? At most 2 to the k. So you need to argue that. So the height has to be. So this means, so this is true for any binary tree. So what is our statement about sorting? First, any sorting algorithm can be modeled as a decision tree. Number 2, with n factorial leaves. Height of such a tree is at least log of n factorial, log of the number of leaves, and the height corresponds to worst case time for the algorithm. So it must be at least log n factorial. And now n factorial, you apply some Stirling's approximation, roughly n by e whole power n. So log of that would give you something like n log n minus n log e or something like that. Okay, so this is a linear term. So any sorting algorithm must perform some omega n log n comparisons. Okay, but do you know any sorting algorithm which can do better? Count sort, radix sort, but how can it be better when I told you that no sorting algorithm can be better than? It's not a comparison based sorting. Okay, this is important to understand. So when I said, you cannot do better unless that unless here would be if you know something about the input, you can count, some range of the values and things like that, you can do better. But the more important thing is to understand this model of computation and this way of showing lower bounds. So again, I think it is not in the exercise. Maybe Madhu, you should add this to the exercise. So for example, if I want to merge a list of size m with a list of size n, can you give a lower bound using decision tree? So let's say mmn is the minimum number of comparisons required to merge a list of size m with a sorted list, obviously. What is mmn is greater than or equal to what? This lower bound. Okay, how do you show this lower bound? What do you need to know? In any decision, so this is again a decision tree modeling. So any comparison based algorithm, you have every node corresponds to a comparison, and if it's less than, go here and so on. And to get a lower bound, what do I need to know? Yes, but height depends on, so you need to know the number of leaves. So count that. Essentially the question boils down to how many leaves are there? How many different permutations of these two lists can you get in the final sorted list. Okay, it's a very simple combinatorial thing. And then you put log on that, you get a lower bound. So the question asks in the problem sheet asks you if m equal to n, you actually have a better lower bound than what lower bound you are going to get from decision tree. Okay, this is also a point that there are, decision tree will give you a lower bound, adversary can give you a better lower bound sometimes. Okay, so when m equal to n, adversary lower bound is better. Better than what? Better than what lower bound you are going to get here by m equal to n. What do you get here? I'm not going to tell you. You have to work it out. Okay. So again, this decision tree can be used for showing lower bounds of sorting, merging, and a number of other problems as well. Okay, final last 5-10 minutes, I'm just going to talk about another problem and appeal to the reduction idea, So one of the powerful idea of reductions is that you can transfer a lower bound from one problem to other problems. That's exactly what NP completeness is all about, right? We assume that SAT cannot be solved in polynomial time. Immediately using all these reductions, you can transfer that lower bound to a number of other problems, right? So, and you've already seen some reductions yesterday, today, and so on. So I'm going to do one more reductions, but in the polynomial level. And here, this lower bound is interesting because it's a combination of adversary and decision tree.
Sir, is there any intuition which method to choose for deciding lower bound in the advisory?
I mean, so typically you can try all of them. Decision tree is something you can easily try because you need to count the number of leaves and you get the height and you see it. And
There might be something that, if this is the case, advisory will definitely
no, there is no such magic, right? It's same as asking, should I use divide and conquer or dynamic programming or greedy for this problem? Well, of course there are some tricks you gain by experience, but there is no magic formula, I would say.
Yeah, I mean not for all, but at least this would fail for sure.
No, all of them will give you lower bounds. Do they give good lower bounds is a question. Right? For example, for max finding, I can say, let me apply decision tree, right? I make comparisons. If it's less than, I go here, greater than, go here, and so on and so forth. And then I find the max. How many leaves are there? N leaves, because there are n possible values for max, n possible positions. So if you take that, the height of that will be log n. Finding max log n, correct lower bound, but not very useful, right? Their adversary is more useful. Okay, so last problem I want to talk about is element distinctness. So the question is, given, I think this is also in the problem sheet, given a list of n elements, n numbers, I want to know, are they all distinct? Okay. And I'm looking at comparison based algorithm because I know usually people say, let me do some hashing and all that, and I don't know how to answer that. Okay. So we are only going to look at comparison based algorithm lower bound. All you're allowed to do is learn something by making comparisons. Are they equal, less than, greater than kind of thing. So can somebody give me an algorithm for this problem? Can somebody give me an n square algorithm? For each element, go through the entire list and compare whether there is anybody else which is equal to it. That's linear time, and do it for n, so that's n square. Okay. Can you give an n log n algorithm? Sort the element and? Oh no. compare with the neighbors. Yes, that's good enough, right? Sort the elements and then look at consecutive numbers and see whether they are equal, because it's not possible that A is not equal to B, B is not equal to C, somehow A will equal to B, C. No, because it's already in increasing order. So sort it in n log n time, compare the adjacent numbers, and that's gives you an n log n algorithm. Now I want to know, can I do better, right? Can we do something better than n log n for answering this question? Okay. If I want to do decision tree, unfortunately the answer is just yes or no. There are only two outputs here. So decision tree doesn't, okay, so to answer your question, right, what applies? Decision tree doesn't look like a right approach here, because there are only two answers here. You're not asking for some element, or are they distinct or not? Hmm?
If you're on diet, it's okay.
Yeah, so now I want to give an adversary lower bound, but the adversary essentially will tell you that, oh, if you answered this question, you know enough to sort. That's the way I'm going to argue, right? So okay. So more precisely, what is the reduction I'm doing? You have n numbers to sort. I give it to this algorithm and ask whether are they all distinct or not. And I want to argue. So it's a very subtle thing. It's not just adversary. It's not decision tree. It's a combination of both. It says that if any algorithm which answers this question must know enough to sort, it must know enough between every pair of numbers. Okay, is the argument statement clear? I want to say that to show that omega n log n is a lower bound for this, the claim is that, yeah, then you know that not all elements are distinct. Yeah, right. So how much time? So I mean, this is same as what somebody was saying. For every element you have to do it. To do the
But if I can scan the array like n.
yeah, right.
And I can get like there are distinct elements or not.
Yeah. How much time? I mean, not, for every element you have to do a scan to see the count of this element. Now go to the next element, you have to do a count.
If I do this, so I am taking one element. So I am getting a new element. Okay, counter 0 to 1. Then I am going to the next. Okay, this is one new element.
How do you know? How do I know it's a new element? You have to compare. Then only you know it is the same element or a new element, right? Yeah. Okay, so my claim is that any algorithm to answer this has enough to sort. Okay, this is, yeah. So, you run this element distinctness algorithm, and I claim that during the process, the algorithm has learned enough between every pair of elements and it knows the sorted order. Suppose not. As an adversary, what do I want to argue? Suppose, let's say, between some pair A, B, the algorithm does not know whether A is less than B or A is greater than B. Then what I will argue is that I can make A and B equal or not. I have a choice. This is exactly the adversary argument for max, I said, right? If you played less than n minus 2 comparisons, I can make this the max or this the max. I have a choice, so I can prove you wrong. So there is an input for which you will be wrong. So similarly here I'm going to say, if you have a pair of elements about which you did not know anything, then I have a choice of making those pair equal or not, consistent with whatever I have answered. That's important, right? I can't arbitrarily change this where if I might have answered something else before. Okay. Then for all x not equal to a comma b, I claim that the relationship between a and x, if I had answered, and b and x are the same. I will not have said that a is less than x, but b is greater than x. Is not possible. Why not? Based on whatever I have answered, pick any x which is not equal to a or b. My answer between x and a and x and b must be the same, whatever I have said. It is not possible that I said a is less than x, but somehow b is greater than x. Because if these two are true, then what can I conclude? A is less than b, but I know that this is not known, right? So similarly, I could not have answered a is bigger than x and b is smaller than x. In that case, I would have known this. Okay, so that means these two elements in the linear order are behaving in the same way with respect to everybody else. So I have a choice of making it equal or not equal. That's all it says. Okay, so it's a combination of adversary and reduction from sorting. That means if you did not learn anything between A and B, then it doesn't know about whether all elements are distinct or not. Because I have a choice of me. For these two input, algorithm would have given the same answer, which is wrong. One of them, it's wrong. Okay, I think I will stop here. So what we have seen is that these algorithms cannot be improved substantially. Maybe, and by the way, for sorting, it's still the exact constant. Here we are talking about three. We didn't say linear. We only worried about the exact constant. The exact constant for sorting is still not completely resolved. Okay, but at least in the bigger world, you cannot do better than n log n. And then in the later lectures, you are going to see, more negative results about certain things cannot be improved under some assumptions. And that's what, and then we will worry about what else can I do, and that's what the algorithmic approach is about.